Hi, in today's video we're going to talk about differential equations. So what is a differential equation? Differential equations are equations that relate a function with one or more of its derivatives.
For example, d2y over dx2 plus 3 dy over dx equals to 4y. This is an example of a differential equation. Another way to write this in the form of a function of a x would be f double prime x plus 3f prime of x equals to 4f of x. This is how you would write it in the function of x. Another way to write this differential equation would be y double prime plus 3 prime of y equals to 4y. These are all the same differential equation. Usually, a differential equation will follow this format. dy over dx equals to an algebraic.
In some cases, you'll be asked to classify your differential equations into order and degree. So let's start off by defining order and degree. First order differential equations are ones that contain only first derivatives, while second order differential equations are ones that contain second derivatives. And the degree of a differential equation is the highest power of the highest derivative. So in example A, you can see that there's a second derivative and a first derivative. And because there's a second derivative, it belongs in the second order. And the power of the second derivative is 1, so its degree is 1 because the second derivative is the higher derivative. And so in example B, there's no second derivative but only a first derivative, and that makes it automatically the highest one, so its degree is going to be 5 because its power is 5, and because it only has a first derivative, it belongs in the first order. Let's go over some general concepts about differential equations before we get into examples. So the goal of solving a differential equation is to work backwards from the derivative to the function. And so if you have an equation in the form of y equals f of x plus c, since the technique involves integration, it's going to have a general solution, not an actual value as a solution. It's going to have a constant integration. But if the value of the function is known at x, that's going to be the initial condition, and then the value of c can be found, it's going to have a specific solution.
For example, in the following differential equation, dy over dx equals to x to the power of 2 minus 3. To solve this, first we must move all of the same variables to the same side. So to rewrite this will be dy equals to x to the power of 2 minus 3 dx. Now that we have done this, the next step is to take the integral, or also known as the antiderivative of this side. So y equals the antiderivative of this x to the power of 2 minus 3 dx will be x to the power of 3 over 3 minus 3x plus c. This is known as your general solution. Say, for example, you were given an initial condition from, let's say, 0 to 3. What you do now is you plug in this initial condition to the general solution to find what is known as the specific solution. So you'll plug in your 0 in your x values and your 3 in your y values to solve for this c, also known as a constant of integration. So 3 equals to 0 to the power of 3 over 3 minus 3 times 0 plus c. And now we simplify, which will equal to 3 equals to c. Now, with this value found, now we can rewrite the general solution into the specific solution as follows. Y equals to x to the power of 3 over 3 minus 3x plus 3. This is known as your specific solution. Notice how both of these solutions are a function.
Calculus AB, the only type of differential equations studied are called separable. Separable differential equations are those that can be in the form of f of y dy equals g of x dx. Once in that form, both sides can be integrated with the constant of integration, written as plus c, on only one side, usually the right.
For example, in the following separable differential equation, dy over dx equals to negative x to the power of 3 over 3. To solve this, first we must move all of the same variables to the same side. This will be rewritten as 3 dy equals to negative x to the power of 3 dx. The next step is to take the integral of both sides, also known as the antiderivative. So the antiderivative of 3 will be 3y plus the antiderivative of dy will be a constant c, which we'll say c1. And that will equal to the antiderivative of negative x to the power of 3, which will be negative x to the power of 4 over 4 plus the antiderivative of dx, which will be, let's say, another constant, c2. The next step is to simplify. So first we'll subtract c1 on both sides, and we will be left with 3y equals to negative x to the power of 4 over 4 plus c. This can be still simplified further by dividing 3 on each side. So we will be left with y equals to negative x to the power of 4 over 12 plus c. And that is your solution, also known as the general solution.